Hello, welcome to this video. My name is Parth Patil and I am from SY CSI department from Computer Engineering department. My project is a smart intrusion detection and auto lock system. This project started as a hardware embedded system assignment, an Arduino based door lock with ultrasonic sensor and three buttons. But I pushed it further into a full IoT security platform with a cloud connected web dashboard, behavioral analytics, and remote pin management. In this video, I'm going to walk you through everything: how the hardware works, how the cloud layer is designed, how the analytics engine detects suspicious access patterns, and how you would actually build and deploy something like this. Whether you are a CS or C student, this covers embedded systems, full stack web development, and IoT architecture. Let's move on to the problem. The problem with standalone lock systems. Think about a standard Arduino door lock. You build it, it works. Someone walks close, it asks for a pin, you enter it, the door opens. That's great. But the moment you deploy that at a school, a lab, or an office, you run into three massive gaps. First, there is zero audit trail. If something goes wrong, you have absolutely no record of who accessed the door, when, or how many times someone failed the pin. Second, there is no remote management. You have to physically touch the hardware to change the pin. In a building with 20 doors, that's impractical. Third, and this is one of the actually motivated me, there's no intelligence. The system doesn't know if 3 a.m. access is unusual for that device. It doesn't know if five failed attempts in 2 minutes is suspicious, or just unlocks or doesn't. These three gaps are what Smart Lock IDS is specifically designed to close. Three-layer IoT architecture. Smart Lock IDS solves all three gaps through a three-layer architecture. Layer 1 is the edge hardware. The Arduino Uno running on the Atmega 328P chip. This handles everything in real time, detecting someone with ultrasonic sensor, accepting pin entry through the three buttons, driving the servo motor to physically open or close the lock, and giving feedback through RGB LED and buzzer. This layer works completely offline. Even if the internet is down, the door is still functioning. Layer 2 is the bridge. This is a lightweight Python script running on Raspberry Pi or a laptop connected to the Arduino. It reads the JSON events that the Arduino prints over serial and forwards them to the cloud via HTTP post. It also polls the cloud for pin changes and pushes them back to the Arduino. Think of this as a translator between hardware and internet. Layer 3 is the cloud. A Node.js, REST API, and a PostgreSQL database, a behavioral analytics engine, and a React dashboard. This is where the intelligence lives. Every event gets stored, scored, visualized, and if it looks suspicious, escalated as an alert. The key insight is these three layers are independent. The door still works if the cloud is down. The dashboard still shows historical data if the hardware is offline. Separation of concerns properly applied. Coming on to the hardware components and pin connections. Now let's go to the physical components and how they are wired. The brain of the whole system is the Arduino Uno running on Atmega 328P microcontroller. Everything else connects to it. The HCSR04 ultrasonic sensor is your motion detector. Sends out a 40 kHz sound pulse to the trick pin and measures how long it takes to bounce back in the echo pin. Formula is simple. Distance equals duration time 0.034 divided by 2. We have set threshold at 30 centimeters. If someone comes within that range, the system activates. The three buttons are connected to D2, D4, and D7 using Arduino's input pull-up. This means you don't need external resistors. The internal resistors holds the pin high when the button isn't, and it goes low when you press it. This is the debound stable way to read buttons. The RGB LED has 4 pins from left to right when the flat side faces right. It's red on D3, common ground, which is the longest pin, green on D5 and blue on D11. That's the 200 ohm resistor on the common cathode to limit current. The SD90 servo motor connects directly to D6, which is a PWM pin that rotates from 0 degrees locked and to 90 degrees for unlocked. And finally, the buzzer on D8 gives audio feedback, a single beep for access granted and that 300 milliseconds on-off pattern for 5 seconds, which when access is denied. Coming on to the finite state machine logic. The core logic running on Arduino is a finite state machine or FSM. Finite state machine is design pattern where your program is always in exactly one of a defined set of states and events caused it to move between those states in a controlled, predictable way. This is the right pattern for embedded security because it prevents undefined behavior. The system can never be in two states at once or get stuck in a weird intermediate condition. RFSM has two states, idle and code entry. In idle state, the system is just watching. Every 1000 milliseconds, or as we say, every second, it fires the ultrasonic sensor and measures distance. The distance is greater than 30 centimeters, nothing happens, it moves back. If the distance drops below 30 centimeters, meaning someone is standing close to the door, the FSM transitions to code entry. The blue LED lights up and a 10-second timer starts, and the system waits for button presses. In code entry state, the system reads the three buttons and builds up the input array. Once three digits are in, it compares them against the stored password array. If they match, green LED, beep, server toggles, and access is granted. If they don't match, or if the 10-second timer expires between the three digits are entered, red LED, buzzer pattern, access denied, and timeout. Either of the outcome, the FSM reacts back to idle and waits for the next person. The critical implementation details here is that we use delay for 1 second sampling interval. We use millis. This keeps the loop non-blocking so button reads and serial commands can still be processed in parallel. Coming on to the serial telemetry protocol. Once the Arduino handles an event, it needs to be reported to the cloud. This is done through serial telemetry. Every time the FSM changes state, the Arduino prints JSON string over the hardware UART at 9600 baud. There are four event types. Intrusion detected when someone comes within the range. Access granted when the duration in milliseconds from detection to correct pin entry. Access denied from wrong pin or timeout. And a pin ACK, which is the Arduino's confirmation that it is successfully applied a new pin from the cloud. The duration field in access granted and access denied is particularly important. It's how many milliseconds elapse from detection to outcome. This gets fed into the suspicious scoring engine as the duration anomaly component. An unusual fast entry might mean someone who already knows the pin very well, or it might mean something more suspicious. The Python bridge running on a laptop or the Raspberry Pi uses PySerial to read these new line terminated JSON strings, passes them, and immediately forwards them to the Cloud REST API with the device's API key in the header. Every 30 seconds, it also polls the cloud to check if the pin has been changed by a dashboard user, and if so, sends the set pin command back to the Arduino. One important detail on startup. The bridge always fetches the current pin from the cloud and sends it to the Arduino. This ensures that even after a power cut, the Arduino's runtime pin stays in sync with whatever was last sent on the dashboard. Coming on to the cloud architecture. Let's look at the cloud backend architecture. The REST API is built with Node.js and Express. It has two separate authentication systems, one for hardware devices and one for the dashboard users. Devices authenticate using a 256-bit API key in the Edge device key header. This is simple and reliable for embedded devices. Dashboard users authenticate with JSON Web Tokens, short-lived 15-minute access tokens paired with 7-day refresh tokens stored in HTTP-only cookies, so they can't be stolen via JavaScript injection. Database is PostgreSQL. The most important table is the events table. Every access event from every device is stored here, and its device ID, event type, timestamp with time zone, duration in milliseconds, and computed suspicion score. There is a composite index on device ID and timestamp descending, which makes the time ordered queries the dashboard needs very fast. There is a second index on suspicion score descending for the alerts page. The other important tables are devices, which stores each registered lock unit with its API key and current pin hash. Users for dashboard accounts pin changes as an immutable audit trail for every pin change, and analytics cache for pre-computed hourly heat maps so the dashboard doesn't have to recompute them on every load. For hosting, the API and database run on Render and Supabase, which both have free tiers. The React frontend is on Netlify. This whole stack is free to run for a prototype. Coming on to the suspicion score engine. This is the most technically interesting part of the whole system. Every time an access event is written on the database, the engine computes a floating point score between 0 and 1. Higher means more suspicious. The formula is a weighted sum of three components clamped from 0 and 1. S equals clamp of 0.4 times the off hours penalty plus 0.35 times the duration and anomaly penalty plus 0.25 times the recent failure rate penalty. The off hours penalty checks whether the access happened at an unusual time. The system knows the average hour of access for that device from its history. If you access the door at the exactly average time, the penalty is 0. If you access it 12 hours away from the average, the penalty is 1. It scales linearly in between. The duration anomaly penalty uses these core statistics. It takes the absolute difference between the entry's duration and the device's mean duration and divides by 3 standard derivations. An entry exactly at the mean scores 0. An entry more than 3 standard derivations away from normal scores 1. 0. This catches both suspiciously fast entries and suspiciously slow ones. The recent failure rate penalty is simple. Counts how many access denied events happened in the last 5 minutes before this event. 3 or more failures in 5 minutes maxes the component out at 1 with a strong brute force signal. The weights 40%, 35%, 25% reflect the relative importance of time anomaly, speed anomaly, and failure history, respectively. These can be turned developed. Alert thresholds. Once the score is computed, it maps to one of the 3 alert levels. Score 0 and 0.4 are normal, logged and stored, but nothing else happens. This covers your routine daytime access at normal speeds with no recent failures. Scores between 0.4 and 0.7 are suspicious. The event gets highlighted in the dashboard and included in a daily digest email. This might be slightly off course access combined with 1 or 2 earlier failed attempts. Scores between 0.7 trigger high alert. This event appears prominently on the alerts page with a red patch, and the system sends an immediate email or SMS notification to the device owner. This is one of our future scopes. Let me walk you through the 4 test cases in the table to make this concrete. Row 1. Routine daytime access, normal entry, speed, no recent failures. All 3 penalties are near 0. Final score 0.04, which is normal. Row 2. Slightly off hours, normal speed, 1 prior failure in the window. PR comes up to 0.42, P fail at 0.33, and weighted sum is 0.28. Still normal, but getting there. Row 3. Moderate off hours, unusually fast entries, 2 failures in 5 minutes. Now we are getting PR of 0.67, P duration of 0.71, and P fail of 0.67. Weighted sum hits 0.68, which is suspicious. Dashboard starts highlighting this. Row 4. Late night, very fast entry, 3 failures in 5 minutes, PR near 1, P duration near 1, P fail at 1. Score is 0.94, extremely high alert. Immediate notification fires up. This scoring approach is notable because it doesn't need any training data or machine learning. It's purely statistical, but it starts producing useful signals from the very first event accessed. Coming on to the remote pin management flow. The remote pin management feature is the most complex integration point in the whole system. Step 1. A user logs into the dashboard and clicks Change pin on a specific device's detail page. A model appears asking for the new 3-digit pin. Step 2. The frontend sends an HTTP patch request to API devices with the new pin in the request body. The API encrypt hashes the new pin and scores it in the device table, replacing the old hash. The API creates an immutable record in the pin, changes table. This is the audit trail. Date time, who changed it, device ID, all stored permanently. The API emits a WebSocket event on the device's private channel, pin updated. The Python bridge agent, which is subscribed to the WebSocket channel, receives the event immediately. The bridge fetches the new pin from get and gets back to the plain text pin array. The bridge sends a JSON set pin command over serial to Arduino. The Arduino's command handler passes the JSON, extracts the 3-digit values, and overwrites the runtime password array in memory. And it prints a pin ACK confirmation over a serial. That is, the pin has been changed. The key security property here is that the pin is never stored in a plain text in the cloud, only as a bicrypt hash. The plain text only exists in the Arduino's RAM and during the brief serial transmission between the bridge and the Arduino. Coming on to the dashboard pages. The web dashboard is a user-facing interface for everything in the cloud layer. Let me walk through its 6 pages. The overview dashboard is the landing page far after login. It shows summary cards, total devices registered, events today, high alerts, and offline devices. Below that is the real-time event feed. New events from any device push it live via the WebSocket, so you can literally watch their activity happening in real time. The device detail page is the core monitoring view of a single device. It shows the full paginated event log with filters by event type and data range. Suspicion score timeline chart, so you can see if a device pattern are trending more suspicious over time, and the early access heat map, which is 24 hours program. The analytics page aggregates across all your devices, average entry duration over time, access frequency by hour, suspicion score trends. This is where you would spot a device that will persistently flag suspicious events. The alerts page is filtered by showing only events with a suspicion score of above 0.7, sorted by most recent. Each row shows the device, timestamp, score, and which components drove the score high. The pin change is a modal available from any device detail page. You saw the complete flow on a previous slide. Coming on to the deployment and the tech stack. The deployment model uses a split across three free hosting platforms. The React frontend goes on Netlify. This is a static file, so it's always fast and free. The Node.js Express backend API goes on Render. It has a free tier, but it spins down after 15 minutes of inactivity. So the first request after a period of no traffic takes about 30 seconds, which is fine. Socket.io handles reconnection automatically, so this is acceptable for prototypes. PostgreSQL database goes to Supabase instead of Render's built-in database. So the Render deletes the free tier database after 90 days, while Supabase free tier persists indefinitely. For the hardware bridge, you have two options. During deployment and demos, run the Python script on your laptop, which I am doing currently. For permanent deployment, it needs another hardware known as the Raspberry Pi. Zero sitting next to the Arduino, or upgrade to an ESP32 coprocessor, which has a Wi-Fi module installed with it. The course configuration is sometimes students often miss. You must explicitly configure Express backend to allow requests from Netlify domain, otherwise the browser will block all API calls. In the Netlify environment variables, you must point to your render backend URL. The total hardware cost is around 800 rupees. Software stack is entirely free for the prototyping. Coming on to the results and validations. The embedded FSM was tested across 200 authentication cycles in every single CS. The state machine transitions correctly. Idle to code entry on detection and back to idle after outcome. 10-second timeout was enforced within the plus or minus 50 milliseconds. No undefined state was ever observed. For the cloud telemetry, end-to-end latency from the moment of the Arduino prints the serial JSON in the moments in the PostgreSQL database averages 340 milliseconds over standard Wi-Fi connection. Remote pin changes propaganda from the dashboard clicks to Arduino runtime password update in an average of 2.1 seconds. This includes the WebSocket event delivery, serial transmission, and ACK round trip. The analytics engine was validated against synthetic event sequences with known anomaly profiles. The scoring formula correctly identified all 4 test cases categories. High suspicion events were correctly escalated with routine events stayed near zero. Comparative analysis shows that the proposed system is the only one in the comparison that has all 5 features together. Offline authentication, cloud persistence, remote pin management, behavioral scoring, and hourly heat map, all under 800 rupees of hardware cost. This is amazing. Coming on to the conclusion and future work. What this project demonstrates is that an 800 rupee microcontroller project doesn't have to stop at a hardware level. By adding a thoughtfully designed software layer, you get something that's genuinely useful for real security applications, fully auditable, remotable, manageable, and behavioral intelligent access control system. The 3 key contributions I would highlight are: first, the complete 3-layer IoT architecture with proper separation of concerns between edge, bridge, and the cloud. Second, the behavioral and suspicion scoring formula that starts producing useful signals from the very first event with no training data required. And third, the bidirectional pin synchronization that closes the loop between cloud management and physical hardware. For future work, the most impactful improvement would be replacing the Python bridge with an ESP32 coprocessor that makes the system fully standalone without needing any host computer. After that, adding the camera module to capture a snapshot of every intrusion detection would be significantly a security upgrade. On the analytics side, once a device has accumulated enough access history, replacing the statistical scoring with LSTM sequence model on access time patterns would improve accuracy. Thanks for watching. The complete source code, circuit diagrams, and IEEE paper draft will be made available. Thank you for your time.